Good morning, everyone. I'm Chick Howe, Director of Marketing at Swagelok, Denver, and Casper and Grand Junction. Um, I want to thank you all for attending today. We're going to just wait a minute or so. We've got about 20 folks. We're expecting a handful more, and we'll get underway. By way of introduction, joining us today are Joe Rodriguez, uh, thoroughly masked up and ready for anything that comes his way, and Cody Hildebrand, who is also unmasked but equally ready for anything his way. Joe is a 13-year senior applications engineer at Swagelok Corporate, and he's out in Solon, Ohio, joining us from there, and is hip deep in the world of gas distribution systems, and hopefully we can all learn something in that process. Cody Hildebrand is our regional field engineer and general bon vivant. He's been with us for about 8 years now, and I think he's seen just about anything that Colorado and Wyoming can throw at him by way of fluid systems, components, sub-assemblies, et cetera, et cetera, et cetera. And we're going to be talking today about safety and efficiency of gas distribution systems. I know a lot of you have seen some of our advertising that's going out. We've been getting a lot of good feedback on the topic, and it's a pretty significant, in our opinion anyway, advance in terms of how you can build and manage your gas distribution systems both safely and efficiently. So a couple of housekeeping things. There's a Q&A at the bottom. If you have questions, please feel free to throw them in there. There's a chat also there. So if you have something with a little more urgency, throw it in the chat and you can raise your hand and we'll get right to you. We handle these in sort of a conversational fashion. So if something's important to you, it's important to us, and we'll get to it and handle it ASAP. So having said that, I'm going to turn it over to Joe and Cody, and take it away, gentlemen.
All right, good morning, and thank you, Chick. Really appreciate it. As Chick mentioned, we're here to talk about our new gas distribution program, and I guess we'll just hop right in it here. We've already talked a bit about the Q&A, but again, we do encourage you guys to post any questions you do have in the chat. We'll get to them as soon as we possibly can, and we're looking forward to some good back and forth. This presentation, I'm hoping won't take the entire time, so there'll be some time for some good conversation afterwards. All right, Chick already gave a bit of an introduction. Hi, I'm Joe Rodriguez. I've been with Swagelok for 13 years. I have a master's degree in mechanical engineering, and fluid system design has sort of been my bread and butter the entire time I've been with Swagelok. So, we had a really great opportunity to put together a nice application solution program here, and we're looking forward to talking to you guys a bit about, first of all, what is a gas distribution system, and why are they important? Why should you care? We're going to talk a bit about some of the benefits and advantages that we have with the gas distribution program that we've rolled out. We're also going to do a little bit of a primer on pressure regulators and how that affects the performance of your gas distribution system. And we're going to talk about how some of our standardized designs can help you address and avoid the terrible, terrible problem of leakage. We'll finish up with some Q&A. So first, what is a gas distribution system? Well, as it pertains to our program, we consider it the entire network of tubes and components that take gas from whatever your source is, be that a cylinder or cylinder rack, to wherever it's being used. In these illustrations, we have a couple of examples of some common ones. On the left, you see a typical laboratory setup with cylinders sometimes mounted outside in a safe location, depending on what sort of gases are in them. A couple cylinders bench side for some of the more inert sort of things. On the right, a very common analyzer shelter. You'll have carrier and cal gases out there to help feed your process analyzer. Gas distribution plays a significant role in the operation of both of those, as well as other facilities. Typically, you'll find gas distribution panels in any sort of on-site laboratories or operations spaces. Um, we find them also frequently in government research facilities, university research facilities, gas companies and medical facilities, and I'm sure many other applications that we are too numerous to list. So why would you have a gas panel? Well, typically you'll have a gas cylinder and you need to get it to some place to use it. So the panel typically have some regulation right there by the bottle that gives you a nice point to access that gas. It'll reduce that high bottle pressure and variable bottle pressure to some sort of a lower constant, typically for a transport line, and carry that into the facility at a more safe uh, sort of pressure. Uh, you can also choose gas panels that allow you to have uninterrupted supply of gases. Cylinders have a finite amount of gas in them, and when they do empty out, you can experience interruptions while you're changing, but there are ways to design a system to help avoid that. You'll typically use gas panels to handle reactive, toxic, or corrosive gases. Again, bringing those down to safer pressures for transport into the facilities. Um, and it usually offers your system the ability to be designed modularly, so you will have a bit more flexibility to tailor your gas system to what your particular application may require. So overall system advantages with gas distribution, the goal is to improve safety. Uh, you want to also maximize your resources. You don't want to have a lot of people dedicated to servicing and maintaining these things. You want to increase your uptime and reduce your maintenance and running costs. We're going to take a brief moment here and talk about the fire triangle and safety, particularly when it comes to, say, oxygen systems. Oxygen, as we know, is a very common industrial compressed gas, but it does need to be treated with some care. What we generally consider primarily with oxygen systems is the risk of fire, and everybody's familiar with the fire triangle. There are three things that the fire needs in order to be able to start and sustain. You need to have an oxidizer. Commonly, that's oxygen, but not necessarily just oxygen. Could also be fluorine, nitrous oxide, and other compounds. Typically, you can't get away from having those. Um, you'll have to have a fuel. So this could be anything from contaminants inside your system, be those particulate or oils, as well as any sort of plastics or elastomers, sealing materials that are in your system. And at higher pressures, even the metals themselves can become fuel for a fire. And the other leg of the fire triangle that you need to mitigate and manage is your ignition or heat source. So if you can manage to take away one of these legs of the fire triangle, you can mitigate your risk. And typically you're going to focus on reducing your ignition source potential. Um, commonly with our oxygen systems, there'll be two things that you'll target. It'll be a particle impact, which is if there's small particles floating around in your oxygen system and they run into the wall of, say, a T or a valve body or something like that, they'll typically impart a little bit of energy. And if that energy is high enough, you can auto ignite that particle, which then can cause a fire. You'll also be worried about compression ignition or adiabatic compression. So if you have, say, a cylinder that you open very rapidly, that can compress the gas that's downstream. And if you compress it quickly enough, its heat will raise, its temperature will raise. And if it approaches the auto ignition temperature of any elastomers, say, for example, a valve seat in your system, that can also cause an ignition. So the GDP has very specific oxygen system designs. If in the event that you are choosing an oxygen configuration, we do our best to mitigate all these risks, and we have a number of safety features that are built in. So we have oxygen tested regulators. They're tested to ASTM I think it's G175. We also have oxygen tested filters. Everything will be made of burn resistant materials that are cleaned, especially for oxygen use. We also make use of slow open valves and heat dissipation tubes to ensure that any sort of risk of auto ignition due to adiabatic compression is reduced. We talked before a little bit about changeovers and how they can help you out. Typically, when you have a cylinder or a pair of cylinders in service, when you have one that empties itself out, if you then have to manually disconnect that cylinder or manually switch a valve over to a second cylinder, you can experience an interruption in your gas supply. If you have a process that is not tolerant of that sort of interruption, you could use an automatic changeover. And we have a system specifically designed to facilitate that. It's driven by a pair of regulators. And what they do is they will automatically pull from a primary source until the source is depleted. And then without any operator interaction, it'll automatically switch over and start using from a secondary source. So that'll provide you the opportunity to change your initial bottle without interruption of the supply of gas to the rest of the system. These systems, and I think you'll find that all of our gas distribution systems are highly configurable. And in addition to the hundreds of thousands of possible configurations that you can pull out by standard, you can also customize any of these systems to suit any particular needs you have. So if, for example, you need to have an alarm or some sort of automation to let you know when a bottle needs to be changed, that's certainly something that Swagelok can help you with. We spent a fair amount of time in the design of the gas distribution systems to make sure that we had adequate filtration. One of the common pain points that we've heard about with regulators and gas systems is contamination on regulator seats. And this, again, causes unplanned interruption when you have to take down the system, pull out the regulator, replace the seat, and then recommission. So we've used Swagelok K-series regulators, which feature a filter on their inlet. Typically, this will be something like a wire mesh. In the case of oxygen systems, it'll also have a bronze sintered element. But we also have a T-style inline filter that's available as close to the cylinder source as possible as standard. Again, all in the name of making sure that you're keeping your regulators up and running. Generally speaking, you do want to try to match your filters to the test that you've got in place. And I do believe we have a poll available for you guys at this point in time. We're curious to know what sort of things you guys see that cause interruptions with your gas distribution systems.
Timing is exquisite, Joe. Thank you. So we'll put this poll up, take a minute, answer it. No right or wrong answers, obviously, but we'd really be interested in hearing the kinds of things that you're running into in terms of the challenges that are being faced with some regularity in your distribution operation. All right.
All right. Looks like we're getting some great responses here.
Sure are. A lot of participation.
It's like watching a horse race.
It is. It's really cool to see it in real time. Do all the participants get to see it in real time, or just us?
You know, I don't know. We could ask participants.
All right.
All right. It looks like we're pretty much there. Well, contamination wins by a nose, followed closely by system design, and then improper sizing and material compatibility. Not unexpected, I don't think, gentlemen. I don't know what your experience is, but it looks like some of the things we had talked about.
Yeah, that looks fairly much in line with the feedback that we've heard from various parts of the globe. We know contamination is a common problem, um, and that can come from a variety of sources. Frequently, when during installation, you're cutting and facing tubes, and it can be very difficult to thoroughly clean them. Um, but system design and sizing, we've also seen a lot of issues with that. Um, I think one of the benefits of the Swagelok gas distribution systems is that they are pre-designed, and they're available with a variety of different flow sizing to handle a variety of different situations. But the thing that we don't want to overlook is that we also offer engineering services. So you can reach out to Swagelok Denver, and they have trained field engineers like Cody who are able to come out and help assess your system. All right.
Okay. We had a couple quick comments here. Nick Green, we threw it out there. I think you should have seen it. It didn't come real time, but you should have seen the poll. If you didn't, let me know and I'll put it back up. Brigham McLaws, what is the name of the automatic switching regulator? Joe, Cody?
That's an excellent question. So the automatic switching regulator that's part of the gas distribution system is called the SCO. We're actually going to get to that a little bit later in the slide deck. So great question.
All right. Looks like that's it for the moment. So let's press on, gentlemen.
All right. So we're going to talk a little bit about some of the basics of regulators. They're pretty important in your gas distribution systems. It's a mechanical device that in our cases is concerning itself with regulating the pressure downstream of itself. Um, so you'll have some changing pressure conditions upstream. So you'll say you've got a cylinder starts out at something like 2200 psi. You may use it down to 50 psi. Well, that's a pressure change that's occurring, and the regulator is there to ensure that the downstream pressure does not change or changes as little as possible over the use of that cylinder. There's some important aspects of
Hey,
regulator performance.
Joe, just if you don't mind, there was just
Oh,
one last chat that came in here. John
yes.
Moffat, and John, we'll make sure to get back to you on this, but he has a challenge for natural gas delivery that has a reduction station to take 600 psi down to 60 psi. So he needs to rebuild a skid. So Cody, I guess you and Don will probably get back to John because I believe he's at Natural Soda. But John, we got it, and we hear what you're saying.
All right.
Sorry for the
Love to
interruption.
see those opportunities. All right. So when you're looking at regulators, typically the thing that you'll go to understand what the regulator's performance is doing is you'll look at the flow curve of it. We have an example on the right. You'll have typically your horizontal axis will be flow, and your vertical axis will be the outlet pressure. Um, And if you look at the far left end of the graph at a zero flow, you'll have an outlet pressure that represents what the regulator might be set at. If, for example, you're first starting up your system, you have your outlet valves shut, and you're just trying to dial in a pressure. In this case, something like 75 psi. But then you'll notice as you begin to have a little bit of flow demand, the outlet pressure will drop, and that's a perfectly normal phenomenon. There'll be a bit of an initial drop that we call the lockup region of the flow curve. That's the small curvature that you see on the left. And then once the regulator gets out of lockup and it begins flowing, it'll be in what we call a bit of the ideal operating range. So it's a reasonably flat flow curve. It'll depend on the particular regulator that you're using, but that can extend very far out. But there will come a point at which the flow demand is too great for the size of the regulator, and this kind of speaks to the improper sizing of components that you guys have been seeing in some of your systems. If you ask for too much flow from a regulator, the pressure that it's delivering will drop very rapidly, and in that state, you're in what's called choked flow. So the gas is essentially traveling at sonic velocity across the regulator seat. The regulator is as wide open as it can get, and it just can't give it any more. So generally speaking, it's good to have an understanding of what the flow demand of your system is, and it's important to choose your regulator size to keep it in that ideal operating range.
Joe, when a regulator is operating at sonic velocity, um, even if it's all the way open, does the pressure always diminish all the way close to zero, or does it often balance out at, just some steady state value?
It won't always drop immediately to zero. I think what you'll notice is if you're in a choked flow condition, as you begin to ask for increasingly uh, large flow demands, the pressure will drop very rapidly. So, great question. All right. So let's talk about the Swagelok gas distribution system offerings, and we're going to have another look at that lab that we were looking at before, because this is a great little show and tell tool. We've looked at a system from all the way from the cylinder source to the point of use, and we sort of broke it down into 4 subsystems that each have a different role to play. So we begin with the source inlet on the top right, and this is what connects your cylinder to the rest of the system. We'll get into a little bit more details on how we do that in a minute. After your SSI will usually be a gas panel, regulator panel, and you have 2 options for that. You have the SGP, which is what you'll use if you have a single source that you need to regulate down. Or we have the Swagelok changeover. This is the SCO that we were just talking about that automatically changes from one source to the next. You'll use this if you need to have an uninterrupted supply of gas, and you'll have 2 inlet sources going to it. And then finally, we'll finish up at the point of use panel. This is what'll take the pressure down from whatever your transport line is to typically a low pressure that's used at whatever sort of tool or device that you need to supply the gas to. So starting at the start with the source inlet, or the SSI, once again, this is to establish the high pressure connection between the cylinder and your first stage of regulation. This is configurable from 1 bottle to many bottles. And if you have many bottles, it'll sort of automatically configure itself into a manifold like you see here. The one that you're looking at is kind of optioned out to the nines. It's got a variety of uh, individual bottle isolation. It's got a main isolation valve. It's got overpressure protection. It's got a relief and a purge on it. One of the key features of these is all of your SSIs will come with an inline filter. Again, we wanted to keep filtration as close to the cylinders as possible to make sure that everything downstream is protected as much as possible. But you can have that also without most of those options, except for the filter that's kind of always there. Essentially it can be as simple as a hose going into a filter into your regulator.
Joe, we had a quick question, and I think that this slide coming up, the one that you just transitioned to, might be good to talk about it. The question is, what kind of venting options are there for the regulators? And I think Joe, when you were talking about seat load drop, lock up and the flow curves in general for pressure regulators? I think it's a pretty decent question, especially regarding setting the pressure when there's no flow. If you've got the valve, like in this picture, there's the valve with the black handle that's on the outlet of the regulator with the green handle. If that valve is closed and you choose to set the pressure at some value, and then when you open that valve, the system demands some kind of flow and it reduces the pressure. Most people on this webinar are probably familiar with the fact that you can quite easily increase the pressure by just turning the handle clockwise to bring it back up to the desired pressure, if it dropped pressure in a steady state fashion. But then what happens is, what if somebody closes that valve and there's components in between that maybe shouldn't see that high of a pressure when there's no flow? So there are options for venting regulators. All regulators with a handle like this one and any sort of bonnet that contains the spring to make it function, they need some sort of atmospheric reference if they're not dome loaded. That atmospheric reference is usually just a small hole that's under the handle. And only in the event that the diaphragm fails would the product leak to atmosphere through that hole. But there's other options where that hole is tapped for like an 1/8 inch NPT fitting, and that's called a captured vent. So in the case that the diaphragm fails, if it's a toxic or a nasty or a flammable gas that you don't want to leak to atmosphere, that can be plumbed to a scrubber, to atmosphere outside of a building, et cetera. And there's also a self-venting option, which means that if you turn the regulator handle counterclockwise, let's say you got a no flow condition, you're trying to set the pressure and you're turning the handle clockwise and you accidentally go a little bit higher than the pressure value that you intended. If you rotate the handle counterclockwise, you don't need any other way to vent the gas. There's a vent that's internal to the upper works of the regulator that allows that gas to come out of the hole that's underneath the handle. Or if you have the captured vent, it would come out of that captured vent hole if it has both a captured vent and a self vent. So if any of you on here have compressors at home, air compressors that you use, most of them come off the shelf with a regulator that has a self vent option. So if you're hooking up some sort of drill drive or something like that that's powered pneumatically, if you accidentally overpressurize it for a few seconds, you can back the handle off and it'll vent out of the hole, and that's what reduces the pressure. So all of those options are available for most of the configurations that we have here, right, Joe?
Yes, absolutely. And thank you, Cody, for the interjection. I don't think I could have said it any better myself. So in addition to venting regulators, your Swagelok gas panel, and I think this also applies to the SCO, the changeover, and the SPU, the point of use panel that we'll get to in a minute. They are available with venting options as well. In the event that you do want to shut off your outlet and you want to vent everything that's upstream of that, it's a little tough to see from the angle here, but there's a little needle valve with a black handle on the left, just to the left of the regulator handle in this configuration, where you can relieve that downstream pressure. They're also available with overpressure relief. You see, this one here is equipped with an R series relief valve, but it's also configurable without, and with a generic placeholder in the event that you want to have some sort of a regional specific, like a safety relief valve that's required for a particular type of service. Another thing I want to mention about the SGP is it does have a variety of outlet isolation options. That would be the small ball valve that you see at the top of this panel. You can have an on-off ball valve, but you can also have a three-way valve. Both of those with locking handle options, which can be really, really important depending on your particular situation. Next up, we have our Swagelok changeover. The key feature of this, again, is that it'll take two inlet sources, and use one of them at a time, and have uninterrupted gas supply downstream. You do have to select these with a particular changeover pressure in mind. So say you want to use your primary source down to 100 PSI, you can specify that in the part number. Otherwise, aside from that special feature, the functionality and options of the SCO will be very much similar to the SGP. So you have all the same venting and overpressure relief and outlet isolation options available to you.
Joe, can you use your mouse cursor to kind of hover over the hub and the handle that's used to manually change them over when you switch the bottles out?
Yeah. So I want to point out a little bit about this. So this right here, this assembly, you can see it's got a little knob that comes up next to the regulator. This is used to determine which of the two sources is used primarily. This is not a manual changeover panel. You don't have to use this lever in order for it to function as a changeover. It will automatically and seamlessly switch from the primary to the secondary. But this is where you'll flip this handle either up or down, depending on whether you prefer to use the left source first or whether you prefer to use the right source first.
And this is, if anybody on this call is familiar with the other changeover, the sort of integrated assemblies that Swagelok offers, the KCA or the KCM assembly. This one's different, and competitive ones, other manufacturers that you may have seen out there. This is different than those assemblies because the two regulators that the gas service changes between as the primary regulator and not the line regulator that steps it down to the final use, they're exposed to the front. So if you're having an issue with one of those regulators, or if it's been in service for whatever your maintenance and repair operations sort of timeline is for a component like this, and you need to change out the upper works of it, change out the diaphragm, change out the poppet, put a new seat in it, things like that, you have access to maintaining it a little bit more easily. And those components should be a little bit more off the shelf. Instead of being more specialty components that would be part of an integrated single regulator body assembly that serves the same function.
Joe and Cody, we have a question from Derek. He doesn't see a check valve on our manifolds. Are they built in with pressure relief valve?
I'm sorry, we're asking about a check valve on the manifold.
Yeah,
Yeah,
so I think Derek is referring to this entire assembly as sort of a manifold. But Derek, I think to answer your question, there's not a check valve that's integral to the relief valve. But these things are all modular, so we can put check valves on it as required, either on the outlet, or if you choose to have some sort of purge gas, be able to be connected to the line regulator or to one of the main regulators, or somewhere upstream on the inlet side of the main regulator. On the hose side, that's the supply side from the bottle, you could have a purge gas, something inert or something like that, if this is for a flammable or some other type of gas that you don't want to have stick around the lines when you go to change the bottles out. So those are all options that's just not displayed in this configuration with those options.
Yeah, and I do want to point out, so these devices that you see hanging down from the two inlet regulators, these actually, those are check valves. So those are there in the event that you do need to change over a bottle. Those are there to prevent any gas from backflowing into the line that you vent out for changing.
And then is there a valve on here that can be used for the venting on this particular configuration?
Yeah, so what you see here pointing more towards the back, these two guys here with the T handles, those are vent valves. So those are upstream of the inlet check valves. So in the event that you need to change over your one of your sources, you'll just open this vent and that'll vent everything out. And you have an option here. So the vents are always there, but you have an option to use this sort of bleed valve, which sort of vents into whatever space this is mounted in. Or if you're dealing with something flammable or something hazardous that you need to not just vent into that space, we have the option to have those inlet vents captured. So those would be switched to, say, a 1 series needle valve that you can plumb up to your flare header or what have you. Great discussion. All right. Well, let's move on to the final stage of your gas distribution system. This will be your point of use panel. This is typically the last bit of regulation that your gas will see before it's going to wherever it's being used. One of the key features of the SPU you'll notice is it's quite a bit smaller than the other ones. It's pretty common to see these mounted very close to one another, either up against a wall or on a lab bench, where there's a variety of gases coming in that all need to service some sort of a process. This one also offers a variety of different mounting options. You can see we've got wall mounts, which is kind of L brackets in a configuration to make an offset wall mount shown here. But those L brackets are universal, so they can be added and subtracted in various configurations in the event that you want to mount it, say, above or below a bench or onto some unistrut. These are available with outlet gauges as standard, but upstream inlet gauges as well if you need to know at the point of use what your supply system is doing. They're available with and without filtration. And they always feature some sort of an inlet isolation there for you. So the gas distribution systems are available with some documentation ready at hand. So these all come with user's manuals that'll guide you through the installation, as well as some of the basic care and feeding and basic troubleshooting of your systems. Your local Swagelok sales and service center can also supply you with sales or as-built drawings, either for the standard configuration or if you've customized anything. Those are available through them very rapidly. And the configurator that we have will also give you a complete bill of materials and a list of the spare components if you need to provide some service for them. Here's just some shots of the part numbering from our application guides. Again, your local sales and service center can help you out with these. But you can see there's quite a number of different options you can select for each one of these guys. So right out of the gate, they're going to be pretty well, pretty able to be tailored to your situation. But as always, if you have special needs or an application that isn't quite met by one of these standard designs, it's should be very straightforward to modify them and get you guys exactly what it is that you're looking for. So speaking of the application guide, that's another one of the bits of documentation that's available for it. We also have available some other literature, a quick look at the program, just kind of a one-pager, as well as a case study from one of our other distributors. I believe this was over in England.
And Joe, we just should note that any one of our account representatives can get this information to you. And I believe some of it's online, but you raise your hand, we'll get you the information.
Excellent. Thanks, Chick. All right. Well, that concludes the presentation portion of it. We've answered some questions along the way. I had a nice little bit of interaction with the poll there. I'm curious to know what other questions and thoughts do you guys have?
We've got a couple open ones, Joe. First question is, do we have an option to add bypass valves?
So the bypass valves are not necessarily one of the standard configuration offerings. It is something that kind of came up during the design phase of it, and there wasn't a whole lot of demand for it at the time, but we do understand, particularly for certain hazardous corrosive gases, that can be pretty desirable for say parallel purging. That's a fairly easy feature to add. So that would be one of the things that we would encourage you to talk with your Swagelok reps about, and they can certainly design a system for that.
Can whoever asked elaborate on what they mean by bypass, like bypassing the entire unit for a point of use or for the source assembly where you're, regulating the main supply?
I don't see anybody coming back to that question. Cody, I have no idea why I can't get you on video, but I will endeavor to continue.
All right.
There was a second question here while this is going on, and I guess this goes back to the changeover system. If it changes supplies automatically, why have a hand valve for your preferred source, specifically the SCO system?
That's an excellent question. Most commonly, say for example, so you'll have two cylinders side by side, and let's say that you're drawing from the left source, and at some point that left source drops down to the changeover pressure, and you start drawing gas from the right-hand cylinder. If you then change your left source and that bottle is now up to full pressure, your changeover assembly is still going to prefer that left source. And so it'll start drawing from the left source again now that it's new, and you'll have a partially depleted bottle on the right. So that changeover handle will allow you to change the right-hand side to the preferred source so that once you've changed the bottles out, you can start drawing from the bottle that's already been somewhat depleted.
Yeah, in other words, you'd be changing the left-hand bottle like 5 times maybe for every 1 time that you change the right-hand bottle instead of
Right.
more evenly.
Derek, I noticed that Cody said you can elaborate, so I'm going to push the magic button here if you want to talk about your question in more detail.
Okay, am I on?
Yep.
We can hear you.
Good.
Here.
All right, good. Okay, thank you. I guess what I mean by bypassing valve is it could be for both application. Sometimes you want to purge the line with nitrogen so we can get rid of all whatever inside the line. Or sometimes we have application that we use water in one line, and then sometimes we wanted to inject nitrogen to push all the water out of the line. In other words, what I'm trying to say is, if sometimes we can add bypass valve to either continue with the loop and changing out filter H2O filters, or sometimes we just kind of like divert the water out of the system. If we, it's kind of like we divide the manifold or the regulator into 2 set of application, one for gas and one for H2O, I guess. I don't know if that is that make any sense?
It makes sense to me. I think that they're all options that would be added on to the base designs. It just depends on what exactly you're trying to do, like the difference between purging something out or purging it out while simultaneously switching over to a different regulation assembly so that you can keep on trucking with the process you've been operating.
Yeah, that's good. Yep. That answered my question regarding the other. And then on your slide, I noted that some of the pressure regulator that with the red indicator that they identified, those pressure. I mean, no. What I mean is pressure relief. Are they engineering to a set point that you ask to make it to a pressure point that it release, or you can adjust it out in the field, or at in-house, it depends on what application or what pressure that I want the system to fail safe and let go of the gas. Is that manually adjustable or is a fixed pressure release valve?
It is ultimately adjustable, but when it's set the first time, there's a lock nut that's set against the cap, and that cap is what's used to adjust the spring, which adjusts the set pressure. So at the time that you order it or you inquire about this kind of panel, we would
Okay.
ask you, well, what do you want that set pressure to be? And, you know, typically, I can speak for myself, I would probably ask some extra questions like, what's the maximum pressure that, you know, the maximum allowable working pressure of the weakest component downstream? Because if you let me know what that is, those relief valves that come on our panels are proportional relief devices. So it depends on what that pressure is, and it depends on what you set the relief valve at, because to discharge any mass, since it's just a simple spring-loaded device, it has to accumulate pressure above the nominal set pressure. So if you set it at 120 psi, it's going to have to be able to accumulate a pressure of plus 10 or plus 15 psi gauge over that pressure to discharge the appropriate amount of mass, whether it be of a liquid or a gas, to keep the resulting pressure under the lowest maximum allowable working pressure component in the downstream part of the system. And there's also a tolerance on that, plus or minus 5%. So if you're taking that plus 5% into consideration, along with that accumulation pressure for the appropriate mass to be discharged, those are all the things I think you got to think about before you pull the trigger on what that nominal value is.
Okay, good. And then do you have the option to kind of like connect downstream of that, like a TL or maybe another two-way valve that you can divert the gas that we want to discharge instead of into the working space? Can we take that and dump it to an exhaust hood or to somewhere outside of the working space?
Yeah, I think it just depends on the application, but for us, I think that the point of this application solution program, or the commercialization side of it, is it's intended to not be something that, you know, you could just go on to swagelok.com, try to configure one of these things yourselves, call up a sales and service center like the one here in Denver and try to order it. Or you could call in and, you know, request our assistance, and we'd help you figure out for your particular routing and plumbing situation, if you have a common header where those exhaust gases go and there's valving on that common header that either makes it go to a fume hood or to a scrubber or to atmosphere or something like that, you could let us know those tubing or pipe sizes, the approximate distances, you know, if there's any elbows or angles in there, and we could let you know if those types of scenarios are going to impact the performance of that particular relief valve in that particular application before you configure it.
Thank you. Then one more question is, up to what size are you currently can work with? Most of our stuff at the lab, we usually deal with either 1/4 inch or 3/8. Seldomly we go to 1/2 inch pipe. So if we need to go to 1/2 inch, are they capable of going to that big and that big of a regulator?
Joe, I'm going to let you run with this one.
Yeah, that's an excellent question. So the standard designs will all use either 1/4 inch or 6 millimeter tubing, depending on whether you're using fractional or metrics for its internal plumbing. Now there are a variety of inlet and outlet connections available, so it can adapt up to 1/2 inch using a standard configuration without a problem. Now, if you have a flow situation where you can't tolerate even a short run of 1/4 inch, for example, if you have a regulator CV of 0.5, where you're really asking for a lot of flow, yes, you can have a custom panel designed that'll have that 1/2 inch tubing internally as well.
Thank you.
Yeah, and those custom situations, and kind of back to John Moffat's question about a natural gas skid and bigger size pressure reduction, those types of things sort of fall outside of the commercialized aspect of this program, but it doesn't mean that the base designs can't be used as a starting point to then just use a different regulator in general. And we have regulators that go all the way up to about 4-inch nominal pipe size, with external feedback to the dome or to a pilot, or can be configured with various let's say more complex feedback control parameters that can make the regulator perform much better in an extremely large span of flows. So we have stuff that can probably supply gas to an entire plant or facility, all the way down to the point of use in a laboratory, on a lab bench, or in a fume hood or something like that.
Okay, if I may, one more. Speaking of natural gas, one of the colleague asked earlier, most of our stuff that we're dealing with air or compressed gas or nitrogen, that measurement in units of PSI. But when we're dealing with natural gas, the measurement is in cubic feet. How do you interchain, or how do you make them together, or somehow that between PSI and cubic feet?
So I understand cubic feet. You're probably talking about cubic feet per minute or cubic feet per second. That's typically a flow rate, as I understand it. And the standard gas distribution panels have pressure measurement on them, but we actually anticipate that there will be instances like you described here where you may need to know the flow rate in addition. So it should be fairly simple to add a flow meter to this system if you need to know how many standard cubic feet are flowing in a unit of time.
Okay. I guess I'm trying to think, is your regulator diaphragm regular PSI, but it's also the diaphragm will adjust and will work with natural gas when we're dealing with cubic feet per minute. Is that making any sense? Most of your regulator is a double bedded, right? I mean, back to back regulator.
You mean like two regulators in series?
No, like
or
I forgot the term.
Regulator, a two-stage regulator where there's
yes,
one
yes, two-stage right there. Yes.
Yeah.
Yes, okay.
Yeah, so the diaphragms are the same on a nominal two-stage regulator. The first stage that it goes through, which you don't have a handle to play with, is set at 500 psi, if I'm not mistaken, Joe.
That's correct.
And then so if the bottle, let's say it's like a bottle of natural gas and some mixture, some specialty gas, whatever it might be. If the bottle goes down to below 500 psi, that first stage regulator is not really going to be doing anything anymore. It's really just a globe style valve flow restriction at that point. But if your question's more about, like, if you're doing engineering design calculations where you say at a given pressure, and we have a desired given volume of gas, what's the equivalent volume of gas at atmospheric pressure that this system would see per unit time? We don't have any devices on there that do like a real-time, calculation output, like maybe like a mass flow controller with a digital output, or an local operator readout would do. But we could always integrate those types of devices into the system for you, again, with the guidance of your input conditions for the application.
Thank you. Thank you.
You bet. Thanks for the great questions.
Okay, we got one more question here. Is the system able to be used outside exposed, or should it be protected? I think that question has a few different answers. It depends on the external conditions. If you're somewhere up in Canada, or if you're somewhere where it really, really, really gets cold, and the plastic on these things might fail on handles, or things like that, or if it rains and sleets and then freezes. I have seen a few situations where outside condensation, like from snow or something like that, might get into the air reference hole of a regulator if it's not oriented the correct way. and that can cause thermal cycling and freezing and then thawing on the sensing mechanism, which could cause it to fail. So those things should be considered carefully. And but normally I'd say down to -40 F, where the scales cross, -40 F, -40 C. These things should be good to go outside, but you have to select the correct elastomers for any of the valving and on the regulators, if that answers the question.
All right.
Well, we've almost
And,
exhausted the hour. I think we ought to let everybody get back to their real world. I want to thank you all for participating. Hope you learned a lot. I know I did. And if you do have any questions, send them our way. Denver.swagelok.com, or actually it's swagelok.denver.com, or your account manager, who will be able to get information to you very quickly. This has been recorded. We will be sending out a link to anybody that both either attended or did not attend, that'll be able to get a look at this. And we did, just FYI, everybody that's still on, we ran into a couple Outlook issues, as well as some security glitch issues whereby people couldn't see the registration button. So if that in fact happened, I know a couple of customers in the government and security areas had this issue. Feel free to share this with anybody you'd like. It should be coming out within 48 hours. So Joe, Cody, any last thoughts before we head out?
No, I just want to thank everybody very much for their time. This is it's been a real pleasure for us to be able to interact with you.
Yeah, thanks everybody for the participation and the good questions, and we look forward to helping you with any of your application troubles in the future.
All right then. Thanks a lot, everyone, and you'll be hearing more from us. There are a few more of these teed up coming for. Well, wait a minute. This just in. Oh, somebody said thank you. Never mind. Thank you guys. Take care.
All right. Take care, everyone.
Thanks everyone. See ya.